So we're going to continue on from our last time was on Tuesday. We talked about section 21, right, where we did ooh, fading a little bit. We talked about hypothesis testing. I think we talked about Welch's tests or Welch's t-tests. We talked about effect size. Is this familiar, right? Oh, we talked about power, right? That was a big aspect that we had. And so those parts. I know we talked also about types of errors, which technically was section 20. But that kind of goes into everything going forward. So these like three sections, sections 20, 21, 22, kind of all blend together, more or less. So kind of like, kind of see where the connections are. In fact, we're going to talk a little bit about sections 21. So if you are currently on section 21, you're probably at the right place because we're going to talk about the second half and then go into section 22. All right. So let me go ahead and I'll go ahead and just share my screen going through here. And so the first thing we're going to talk about, okay, this is where I debated a little bit how I wanted to show you guys. So I'm going to actually make this. We're actually going to talk about ANOVA. And so, no, you know what? I'm going to talk about, I kept going back and forth with this for a long time today. So we're going to talk about multiple comparisons, which is a whole section in the actual curriculum that talks about like, why multiple comparisons are bad. And then also other warnings like unintended consequences. I'm also going to talk about p-hacking. I keep mentioning about p-hacking before. So I think that word probably isn't new to you guys, right? But we'll kind of talk a little bit about like why p-hacking is such a big deal. So multiple comparisons, and I will keep showing this picture because I think it's a perfect example. XKCD, again, is always relevant. I just went on XKCD again, and I was talking about reading books like, oh, this is exactly relevant to like what I'm doing. So anyway, great comic series. But if you can't remember what this picture is, it's very big. Basically, it's the idea that, a person comes up and says, hey, we have a case, we have a hypothesis that jelly beans cause acne. And they investigate it, they do their statistical analysis in the background. Essentially, and they find that P is greater than 0.05, which is the standard of most, statistical analysis, and say, oh, it's not statistically significant. And then they say, oh, okay, well, that settles it, all good. And then says, wait a second, I think it's a certain color. And this is where the key part comes down. So they basically test every color with a t-test, essentially. You can think of a t-test. And they find out pretty much everything has a p-value greater than 0.05. But there's one in particular down this little box right here where they test the green jelly bean, and they find that p is less than 0.5, which means it's significant. And then, of course, the next day, they say, hey, green jelly beans cause acne, which you probably think like, that probably doesn't make sense. And this is one of those things, especially it's very like, I feel like this perfectly kind of shows like what this expectation comes from. And it's because of this guy right here. And XKCD, the Randall, the person who, Randall Moreau, the comics, very smart person. You'll notice that there's 20 total colors they test. And that's because a 0.05 p-value or critical value, right, is 5%, which is the same thing as saying 1/20, right? So basically it's saying that 1 out of 20 times we would expect to reject the null hypothesis when we really shouldn't reject. And that's exactly what you find here. And the reason why this happens, it's not because green jelly beans are actually more important, but it's basically because we're repeating this test over and over and over and over again, where basically there isn't an effect. So we're testing something over and over again that doesn't actually have an effect. We're going to see weird things. There's a book that was suggested at the very beginning of the course, Naked Statistics, and he actually talks about this, like what this kind of looks like, is he talks about when he teaches like a university class, he has everyone stand up and flip a coin, right? And they flip a coin, and once they flip tails, they have to sit down. And so when they flip a coin, say, okay, everyone flip a coin, and they land and say, oh, half the people end up sitting down, right? And then they flip a coin again, and then some people sit down again. And then it's usually by the end, like, he'll have like one person, maybe even more, like flip it 6 times and say, and they'll get like, 6 heads. I think he said like he might even get up to like 8 heads in a row in some cases, depending how big the class is. And he kind of makes the joke and say, how did you know how to flip the coin so well? How do you get heads every time? And it's not that he's good at flipping coins or the coin that he brought in, or she brought in lands on heads every time. It's just out of pure chance. And that's kind of what's going on here. It's just by pure chance, you're going to get values that are very extreme when it really shouldn't be. Another way to look at this is that if you imagine the distribution of like, let's say like if you cause acne, right? I don't know how you measure causes acne necessarily, but if you imagine on this normal curve of causing acne, and let's say, for example, you know, when you test some people actually get like less acne, right? And then some people on the other end get more acne, right? Like just out of pure chance, okay? And then this right here is like no effect. And the problem is like majority, if you test this over and over again, like a large sample, you'd find that most of them would end up being around here. But if you test over and over again, you also have a chance of getting something on this tail end over here. It's very unlikely, but it's possible. And what it's going to look like is that your value is actually extreme when it really shouldn't be. So this is what really multiple comparisons comes from. And so this is something you should be really careful about, is that if you are doing any kind of like analysis that involves multiple categories, you should be very aware that you might actually end up finding a significant result when there really shouldn't be. And this is where we can kind of talk about like how you factor that in. So kind of give you another scenario that's not jelly beans, is that like if you were to give a drug treatment to a patient and you have drug A, drug B, drug C, or even just like drug A, drug B, drug C, but also maybe it affects differently for males versus females. This can affect, you know, what kind of comparison you have, because if you now have, you know, 3 different drug types and then, you know, it can be male or female, those are relatively simple, pretty common. You now have 6 different categories. You have now 6 different chances to accidentally get a significant result when there really shouldn't be. Okay, and this is where that part comes really, you have to be really careful with. And we'll talk about how we can deal with multiple comparisons. There's a link right here. I don't know if anyone's gotten to it yet in the curriculum, Spurious Correlation, which is a great website. Basically, they find correlations that associate with each other that really shouldn't. So for example, it's a little sad, but US spending on science and space technology associated with suicide by hanging, circulation, and suffocation. Which if you are, you know, if you're either ignorant or want to kind of stretch the truth a little bit, you would say, hey, we shouldn't be spending so much on science because people are hanging themselves. They start trying to find these connections together. This is the one that actually, I think, shows in the curriculum, number of people drowned versus Nicolas Cage appeared in. And you can see it's strongly correlated, where the number of drownings increases as more films Nicolas Cage actually shows up in. So we should actually make sure that Nicolas Cage never shows up in any movies, would be the correlation. And this is where one of the reasons why this happens. Well, let me ask you guys, what are some reasons this might happen with these different, and I'll keep scrolling down just so you guys see it. But why might this actually exist? Like, look at this correlation. This is a strong correlation, right? With per capita cheese consumption and people who died by being tangled in their veggies. Man, these are really depressing ones, but you get the point. Why might these exist?
I would say pure chance.
Mm-hmm. And a lot of it is pure chance. Basically,
or underlying other factors. They're not correlate to both things, but not, you know, not both.
Yeah, and you're absolutely right on both of those accounts, Giovanna. Is one, like, it could just be that there's some underlying factor. A famous one, for example, that was a true thing, was they thought ice cream caused polio. And one of the reasons why is because they noticed when people ate more ice cream, they were more likely to get polio. It turns out, though, is that what likely happened was polio was more, during the summer, people were interacting with each other more. It tended to be children, and they also tended to eat ice cream more in the summer, too. So you ended up seeing a correlation where ice cream and polio were connected together. And this is where, like, you know, can be something like, oh, like, you think that there's a cause and effect, but really there's another, there's another factor putting it in there. So that's definitely one part. Another one is what Giovanna said, pure chance. Like, basically, you compare enough things. If I basically have all these different statistics on number of people who died tangled with their bed sheets, and then just look at anything like, you know, per capita cheese consumption, divorce rate in Maine, you know, Nicolas Cage, you know, films that I can probably find something, because I can basically have a wide enough variety where I can find something. And this is actually really important, where you have to be careful about how much you're searching for and being very stringent on saying, is this statistically significant or not? Excuse me. What was I saying now? So this is something like when we do multiple comparisons, we have to be very wary of like what we're doing, right? Because they can look very associated with each other, even though they're not really. This kind of leads us into p-hacking. So p-hacking, there's a whole bunch of things you can do. Again, XKCD, always relevant, apparently. And this is where I think it's really hilarious, is that they have the different p-values. And you guys now know the p-value, usually 0.05 is what we're looking for. And basically going through different scenarios, for example, saying, oh, you get 0.001, these are very, very significant. But if you get a p-value of like 0.5, you're like, oops, like something went wrong, go do the calculations over again. And this is actually really, like this says a lot to what's being done in research, is that if you find a value that's either slightly above or at kind of p-value, you'll have people like, well, maybe I need to get more samples. And the funny thing is, by adding more samples into your, as I think we talked about this before, adding more samples into your hypothesis test, you can actually affect and say by a certain percentage, you can actually get more extreme values and you'll actually get significance when it really shouldn't. If you have many, many samples, let's say you have like this many samples, or, oh, I need more samples, and you get many, many more samples and redo your tests, then you're more likely to actually get a true, a higher truth. But adding just one extra sample or just a few more extra members in your sample can actually make your significance go down on the extreme end. And just by getting more doesn't necessarily mean that you're going to, like, especially when you're on that edge. Because you only, like, think of it this way. When you're at like lower than the p-value, so you have a highest significance, are you going to get more on that sample? No, right? Because you already rejected your null hypothesis. You figured it out. But if you only ask for more when you don't pass that threshold, you're going to find out that just out of pure chance, the times that you stop looking are going to be the ones when you accidentally go underneath that threshold and say it's significant. And so this is where you have to be really careful. And this is where p-hacking, where people either do it purposely or more likely they do it by accident because they're not thinking about this. So there's this good article right here that kind of talks about p-hacking. They have a little bit of code. It's more R code, I think, but it doesn't really matter. There are kind of like these talks about like what things people do to p-hack. So they stop collecting data once they hit p less than 0.05. So this is like if you're doing an experiment and you basically collect data until you hit 0.05 and you stop. This is an issue because obviously you're only stopping once you hit underneath that threshold, right? Another thing too is what happens a lot in science journals is you only report the ones that are actually significant, or at least were tested significant. That can be an issue too because you now have confirmation bias. You're like only reporting things that are actually underneath that value. And then let's do this third part. Collect and analyze many conditions, but only report this. This is similar to this one right here. This one's got a famous background to, like I think I mentioned before, like the guy who purposely, well, he found that chocolate causes you to lose weight, or dark chocolate causes you to lose weight. Have I talked about this before? Okay, cool. So yeah, so that one's like a classic one where he basically measured a bunch of different things, right? And only reported the ones that were actually significant, basically by chance. Covariates, so this is like when things are related to each other. So when one affects the other, so you can get less than 0.05. So this is like the classic, like, you know, ice cream and drownings, you know, like both are caused by summer. So they look like they're correlated together. So this would be covariates. And then exclude participants, same thing, get rid of certain ones that don't, so you get a smaller point value, significant value, and then transferring the data. That's a little more subtle of exactly how this happens. But one thing that this article talks about, suggests about, is how 0.05 is considered our standard. That's our critical value that we always say. It's our false positive rate. The problem is that by using that value, we're basically saying 5% false positive rate that's what we accept. That might not be true depending on what area you're looking at. If you are in the medical field, it might be different versus if you're in physics, it might be a different kind of acceptance of like what kind of extreme value you need. And this is where you have to be aware of that by setting this value in here. In a sense, we're making a new measurement. We're actually saying, hey, and this is a reference to Goodhart's law, which we'll talk about, where essentially everyone's trying to get underneath that 0.05. And we might accidentally do things that cause us to dip underneath those values. So good article to read through. I'll have it linked in the notebook. But this kind of leads us to unintended consequences, which is Goodhart's law. And so it's referenced here saying Goodhart's law, and basically it's usually quoted as, any observed statistical regularity will tend to collapse once pressure is placed upon it for control purposes. Oh, big words, right? Or you can also see it as, when a measure becomes a target, it's no longer a measure. So basically, a big part here is saying when you use that measure as a target, you are more likely, or you're going to not have a good measurement of what's going on. So here's the Wikipedia. So I linked the Wikipedia article in here. The curriculum talks about examples of this is the Cobra part. Has anyone read this section yet on the Cobra problem? Okay, so I'm gonna state this stuff and I'm gonna probably make a mistake on exactly how it's coded, but you get the idea. So basically there was a Cobra problem in, I think it was like in a state or in a city of India. And so one thing they said is like, okay, what they want is people to get rid of cobras, right? So basically they said every time we will pay you amount of money for the dead cobras you bring in. So if you bring in like 5 dead cobras, we'll give you like $5 or something like that, right? Bring 10 dead cobras, we'll give you $10, all that stuff. So what they found, basically, they, well, let me ask you guys, what might be an issue with that? And you guys might already know what this might end up bringing up. Because that seems like a decent plan, right? Is that if you kill more of cobras, if you encourage people to kill cobras, then there'll be less cobras, right, in the city and everything like that. Anyone got an idea where this might go wrong?
People might start breeding cobras.
And yeah, and that's what they found. Basically what happened, they found that people every year were bringing more and more cobras, dead cobras, but the cobra problem was actually getting worse. And what they found out is people were literally breeding cobras to make money off of that. And this is where that metric to say, oh, you know, if we're getting more dead cobras in there should be less cobras in the wild, where basically what happened, you have unintended consequences where these things come up. This happens all the time in any kind of like economic system, and economic meaning that there's some value in this metric itself. So the classic one, for example, is like, you know, sales and stuff like this. If a company says, all right, we need to make more sales and stuff like this, they might start doing things. The idea here is like people will work harder to make those sales, but maybe there's other ways to get around this. Maybe, for example, you essentially start lying, you know, to basically get those sales together, like to do those sales, or more subtle parts where maybe you only chase after clients that are very small. Like if you're doing number of sales, you actually are accounting for only people that aren't buying very much, but are easy to sell to. So like you're only selling like, you know, like you're making a profit of $5 versus like $5,000 because they're easier to make because you're getting more sales, even though you're not getting as much profit. So in that case, like, oh, you should have been using the metric of profit to do that. And this is where, again, Goodhart's law is kind of like always should be in the back of your mind saying, what is the unintended consequences of making this metric, you know, the thing that you're shooting towards? And also saying, is this the right metric? And this would lead us directly into A/B tests. So that's kind of like some overall warnings that are all kind of connected together, and things I think like you should always keep in the back of your mind whenever you're performing a statistical test and saying, is there parts where like, what are the unintended consequences that I might not be seeing right now? Okay. Any questions you guys have on any of this? Goodhart's law, p-hacking, multiple comparisons. Okay, sound good? Hopefully this all kind of makes sense in that way, right? All right, so I'm actually gonna go into now for multiple comparisons. This is technically part of section 21, but we didn't go over it last time. So I'm gonna go ahead and go into this now is ANOVA. So ANOVA, I actually don't remember how exactly everyone pronounces it. I hear both ways, ANOVA versus ANOVA. It's an acronym, it's not a stellar object, it's not ANOVA. It's analysis of variance. So this is basically, what's it called? You're basically analyzing how much your parts vary from each other. And so this is kind of one of the solutions you can have for multiple comparisons. It's not the only way you can do stuff, but it is a way that the curriculum kind of focuses on. So I'm going to talk about it. I will be upfront with you guys is that this isn't necessarily something that is done all the time in industry. This might be more academic in some ways. And there are other ways, for example, usually people approach it directly with an F-test. And this is the stuff where I'm going to just straight up say is that there is so much of statistics that you can possibly learn. I think like when I was kind of going through this personally, I was trying to figure out the best way to explain this. And I ended up going into like a 2-3 hour just like deep dive of statistics. Like I was pulling up like different papers and like, you know, books and stuff and resources and trying to say like, what's the best way to explain this? And I kind of ended up realizing like, you know what? There's a little too much to go on this. Like, I think that's a little too much for you guys to go at once. So I'm going to explain the basis of ANOVA, like what it's doing without using too much math. And then I'm going to show you what the curriculum shows, and then also another alternative to view this with SciPy. Okay, so just kind of know there's a little difference here. So the main thing is like, okay, how does this work? So it's basically another test. It's you calculate a statistic, the F ratio or F statistic, to get a p-value. So kind of similar to how to get a t-value, we can basically get this distribution and we can calculate the p-value from there, which the p-value, again, is the probability of us detecting, rejecting the null hypothesis. Like how many what percentage are we allowed to do a false positive? So if we repeat this test over and over again, what's our value of actually rejecting it? So we want a small p-value so our chance is actually not very large, okay? So basically is, I'm trying to think the best way to approach this right now, is that we're gonna look at a few things. So I'm gonna draw a little picture here because I think that's gonna be the easiest one to do. So imagine you have like some value here. So let's say this is like the, you're testing on some mice, right? And you're testing out like a new diet or something. I think that's a good one. A new diet for each mouse, right? Or set of mice. And you want to see, you know, how much weight gain. So this is going to be like weight gain. So your y-axis will say how much weight gain. And I'm going to break it up into categories versus like on a spectrum. So for example, like going off of this, I'll say this is, for example, you know, no diet. So this is our control. This will be like diet A. And this will be diet B, and let's say the diet C, right? So all of these are like, okay, these are different. They're hopefully independent in this way, so I can test this out. And what you find is that for the no diet, you might find mice hover around this area right here. For A diet, you might see, oh, there's less weight gain right here. Okay, and then for this diet, it's like, oh, you have something along this lines. And then for C diet, you might have something like, it looks like control. Okay, so this is our different groups right here. And so what we could do is we could essentially do a t-test on each comparison from a control and A. So we could, for example, do a comparison from control and A. We could do a t-test on control and B, and a t-test with control and C. Okay, and see which ones are significant, right? Why is this a bad idea? Yeah, so this one it kind of goes into multiple comparisons, right? So I'm doing a t-test for each one, right? And I'll set my alpha to 0.05, right? If I instead had like 20 different diets and I did this exact thing, all right, would you expect that one of those diets just by chance to maybe be that significant value? And I think, yeah, I see Giovanna on a yes, and like, oh yes, this is the same thing as the jelly beans, right? You're basically testing if the diets actually have no effect, and in fact, I test every single one, there's a chance as I increase the number of different diets I have, that one of them will be significant, even though they really shouldn't be, okay? And so this would be an issue, right? So there's a few things you can do. One way is you can do ANOVA. So ANOVA, and I'm gonna do very, like, this is not math. There's a little more complication than this. I just wanna make that clear. But this is the basics of what ANOVA is doing. So we have our different groups, our no diet, our A diet, our B diet, our C diet. If I group them all together, right, what I'll have, and I'll draw this line, this will have the average be like about here. Yeah, that's probably wrong. I'll try to be a little more realistic. About like right here, okay? So that means like half of them are below, half of them are above. So that's the average, right? If I group them all together. And then what you do, you basically take each group and you say, okay, if I look at each individual group by itself, and I'll use a color that's a little different from black, you take the average of each part. So you say, oh, there's the average here, here's the average here, here's the average here, and here's the average here. Okay, and what we want to know is like, hey, does this diet different from the C diet, or any of these diets different from this control diet? Is there a difference in diets? And so what you can do then basically is you would essentially see how much, first of all, each point, how much they vary from, and I'll use black here so that way we can make it clear, how much they vary from the overall mean. So how much do they vary from this part? So you can see this part is a difference from this. This is a difference from here. This is a very small difference. This is a small difference, or a medium difference. And this one you can see, oh, these are all negative differences from this part right here. And so basically we would get all these residuals, right? The sum of squares, like this, how we normally would do it for like linear regression, okay? And we would basically say, okay, that's all the differences here, and we add them all up, and we have some number, right? Some sum of squares difference from this overall mean, okay? Then what we do, and I'll see if I can just kind of erase these parts, okay? Then what we would do for each individual group, we would also find the residuals, the residuals from its personal group's mean. So this group mean right here, well, that means this residual is very small compared to this one. And this one right here, we have other residuals here, and we basically would add these residuals up themselves. So you can see there's going to be a difference between the overall mean and its individual mean. And basically you add this up and you create a ratio of saying the difference of all the sum of squares for all that means, basically how different are they from the overall mean, and then how different are they from their individual means. And basically that creates our F statistic. And with that F statistic, we can actually do an F test and say is it significant. And what's nice, we have handy dandy computers that will calculate that F statistic with our data. And this is where it gets complicated, where there's degrees of freedom that's kind of mixed into this. And this is why I'm not showing you the full math. And basically you take that F statistic and convert it into a p-value, and you say, is that p-value smaller than our critical value? And if it is, if this p-value is smaller than a critical value, you say, cool, that means we actually have a significant difference with the groups. If the p-value is bigger than this, then you say, okay, it means that, you know, there's we fail to reject the null hypothesis and say there probably isn't a difference on this. Okay, so this is the main idea. I wanted to show you what this looks like. In reality, you will not do this like by hand. You won't kind of put this, usually you use a package to do this. But I wanted to show you what this is versus just saying, oh, we're going to perform a test, okay? It does talk about the curriculum kind of very briefly. It says it's a group, I can't remember the exact phrasing, but it's like the mean sum squares of the group mean versus the group mean of means. And it's like kind of confusing, it's just in words. But hopefully you kind of see here is that we're basically combining all of the residuals together and then the residuals of just the individual groups. And I linked here Wikipedia, which actually has a great image of this. And I'm trying to like really hone in the point of like what this is. So there's this image right here, but basically there is no difference. So on this yellow right here, it doesn't really matter what the data is, but basically the distribution shows like they're pretty much, you know, it's kind of a complicated distribution. And I think this was like a dog show is what they were saying, like the different sizes of weights and stuff like this and whether they won or whatnot. But basically, this is the distribution of each groups. And you can see the distribution of the groups pretty much are like, even though they're different, they're not significantly different from each other. And so you would say, oh, there's pretty much no difference in here, very low significance, no fit. And then you can see here for ANOVA, what we're having here, we'd compare for the whole group right here and say, well, how much are the residuals for this overall average? And then we would compare the residuals for each individual group. In this case, you can actually see probably quite quickly, there is a difference in the different like breeds or whatever groups there are. Okay? And the last one shows a very significant part where you can see there's very small variance for these individual groups. Like they're very close together, even though if you collected them all together, you would see there's a huge, you know, spectrum of parts. So this means that the groups are actually, in fact, different from the overall population together. Okay, and that's what really ANOVA is doing here. Okay, does that make sense? Intuitively, yeah, hopefully this kind of like makes sense. If you look at this, if I said, oh, this is the group right here, this is the distribution of the group right here, you could probably realize that this group is different from this group, right? You can see there's not a crossover. When it's over on this one, it's a little less clear where it's connected, like where like you're like, oh, are these groups different or we just got extreme values? Like it's not super clear. And then the last one, the very first one we showed, you can see there's pretty much no difference in that distribution. So this is essentially what ANOVA is doing, but with essentially an F statistic to quantify this to a specific like number and say, you know, how different is this? And this is a ratio basically of how different are they between each group or within their group, and then how different are they on the overall like sample. Okay, so this is one way to do multiple comparisons. So that's kind of the overall like what happens here. There's a few assumptions that you should be aware of. And if the assumptions are not true, you should be very wary of using this test. but one is that the samples are independent. So each group by itself are not correlated with each other. If they're correlated with each other, there can be interference in this way, and this test will not work very well. Each sample is normally distributed population. So basically making sure that the overall population is normally distributed so you have an equal chance of going through here. That's an assumption of actually performing this test. And then the last part is the standard deviations of the groups are all equal. So homeoscedastic, right? And note that if these assumptions fail, it's possible just to use a different test. For example, there is this Kruskal-Wallis-H test. So it's good. ANOVA is very powerful, which is why it's really useful. But we can sacrifice power for versatility. Okay. And again, just a repeat, ANOVA is not really used in industry as much. Mostly we're going to be using Welch's test over things, and we'll say, you know, what we can do. There are situations where ANOVA actually is really useful, but just kind of be aware of what industry practices are. So that's kind of ANOVA, very like broad stroke. I didn't even go into the math of how this works. So the next thing is to actually see some code, right? To see what this looks like. And the curriculum has obviously their, what's it called? Practice in the lab. So I'm not going to go over that. So I'm going to show you a different example. This actually comes from SciPy's part. So I'm actually going to show you how to do ANOVA with SciPy. And then I'll show you what the curriculum shows with stats models. I'll talk about what the difference is between those two. So I'm just going to import my libraries. And so this is some data actually that comes from this reference right here. So just know this is just random data. This actually is like the shell length. It's a standardized, they standardize the numbers, but basically it's the shell measurement of like, I think it's different like mussels, like, you know, like oysters, mussels, right? So in different areas. So Telemark, Newport, Petersburg, these are different areas where they found these mussels, and these numbers represent a standardized, you know, how much they differed from the overall average, like the shell length, just so you have. And so I'm just taking this data and I'm making it into a nice data frame, right? So you can see here, the area is what city it is. I probably should have just called it city, but oh well. And the shell standardizes the actual number. So for example, if I go ahead and show you what this looks like, you would see that all this data is right here, and you can see Telemark and then the actual size. So these are the different values right here, okay? And then there's an area here. So, okay, so cool. I have my data frame of values and our different classifications. And then what I can do here is I'm gonna go ahead and plot this out. So I thought this would be a nice thing for you to see, is that right now I'm basically using Seaborn to do a box plot. So I'm showing the different distribution, kind of similar with the analysis of variance right here. So you can kind of see how we kind of have this distribution. I'm kind of showing here, and these yellow points right here with the swarm plot from Seaborn are just showing the actual data points for each group. So you see Telemark, Newport, Petersburg, Magadan, I don't know how to pronounce that right, but the different areas, right? And this is the distribution. So you can see the distributions are kind of varied, but you know, it's not super clear if they are in fact different from the population. Does everyone understand what I'm looking at this part? Cool. All right. So this is one way to do it. Box plots are cool. They're very useful in this way. I put some notes in here of what's going on here. I use the color aqua and orange because I know for color blindness, for example, they do really good contrast. If you have red green color blindness, you're not going to have those confused. So it kind of stands out a little bit more. Also, you can change, I don't think I have it on here. Oh, no, I do have it. Alpha, you can change the transparency of those things and the different sizes. So just kind of like know these are things that you can play around with and change. Okay, and a similar one is violin plots. So that also show distribution. And you can see here, you can hopefully see the similarities of like distribution in that sense that I like violin plots a lot because it's kind of similar to our distribution, a histogram on its side, right? And so you can see here, basically it's symmetric over, and the swarm plots show where the actual points are. So you can see, for example, we have a little bulge here because there is a point over on this side. And these violin plots represent basically, oh, if you, maybe there's some few over here and there's nothing right here. If we added more points, we might see this more smoothed over. If you want to, on a violin plot from Seaborn, you can actually change this BW, which is, bandwidth. So basically how much like you want to increase it. So for example, I change it to 9, you see it'll smooth out a little bit more. So it's a little more maybe realistic of the actual data. If I have a lot of data, I might want to change the bandwidth to something smaller to emphasize that, oh, these points are really isolated by itself. But this gives you an idea of the distribution, okay? And so the idea here is hopefully we actually see these distributions are actually different statistically. And so SciPy has a stats package, right? We can use the F one way. So F stands for F tests. And basically I'm comparing, in this case, I'm just using, let's see here, these values directly. I could have also done DF of those areas. So I could have also done like a DF and basically get in just the ones that are in those areas. But now I'm going to compare Telemark, Newport, Petersburg, Magadan, and Tvermine. I don't know. Amin. I'm not here to pronounce things. So very exciting. We actually run this and we get numbers. Okay. So here basically is our F statistic itself, 7.12, which means absolutely nothing to you if you don't know what the distribution is. Basically, this is saying, you know, where it falls on the distribution of the F, from the F statistic. And so usually, since we're using a computer, we actually convert this to the p-value. Note that if you took any like statistics back, like in high school or college, you probably did like look up a table. You would normally take this value and look up on the table for degrees of freedom to figure out, you know, what p-value or significance value can you actually reject. But since we have a computer, we can do that. They can do it for us. So we have a p-value that's very, very small, 0.0002. So we can probably reject this at a very significance level. So that's kind of like, this is your essentially an ANOVA right here, just to kind of make this clear. This is your F test. So essentially this is telling us, oh yes, there is a difference between the groups. Okay. Any questions on what I kind of showed? Okay. The funny thing is that this right here is the whole thing of ANOVA. Like I said, you're not going to do this by hand. You're probably going to use this in a package, or at worst, you make it yourself and probably just reuse it over and over again because you're doing the same test over and over. An alternative, which is what the curriculum shows, is using stats models, OLS. So OLS, remember, is ordinary least squares, right? This is basically just saying it's making a linear model, a linear regression model, and using that to figure out if these fit. And this is where like this is where I got really deep and be like, where I took like way too long last night to say like, how do I explain this? And I said, you know what, we're not going to worry about it too much because there's a lot more that we can talk about because we haven't reached this aspect. But just know that basically this ANOVA relies on the fact of what kind of model are you using. We haven't talked about interactions, but for example, if you have different categories that can affect each other and interact with each other, it's no longer a simple linear model like we've seen before. We'll see this in module 4, somewhere around the beginning of that. But basically, just know we're creating like a model, a linear regression. Here's our Y value. This C represents saying it's a category, so it knows, oh, it's not a value, it's just a category itself. If I had other values in here, for example, if there was another thing like temperature, I would do something like temp, like whatever it was in the data frame, and that would include to basically make our linear regression. But since we only have one value, it has this category, and we'll basically take this linear model, that's what this is, we'll fit it against our data, and then it says from that linear model that we created, go ahead and perform an ANOVA with the linear model. In this case, I'm just putting it in here. And if we print this out, we'll actually see there's a little table, and you'll see right here is our F statistic, which is the same up here, and then our p-value right here. Okay, and so this is what you would be looking for. Basically, this right column is what you'd be looking to say, can I reject that area? Does area actually matter for the shell length in this case? You could also have multiple parts. If I had temp here, for example, if I had like plus temp, there would be another line that would have also a probability on here. And that would say, does temperature by itself matter? Now, of course, I could also have where maybe the area interacts with the temperature. We haven't talked about this, but those things could interact together. Maybe they do really well in cold environments in Newport, but when the temperature is really high, it actually does really well in Petersburg. So those are interactions that you might have. We haven't really talked about this yet, and again, this will be in the next module. But know that that could be another model you could be testing against your ANOVA, right? So basically, just know for ANOVA and the curriculum is that you're really looking at this side right here, and you're saying, is this different? And this is a way to do multiple comparisons. Right? Any questions? I know, like, I kind of glazed over a lot of parts, so feel free to ask if you're like, wait, why did we do this? Cool. Okay, thumbs up if we're feeling pretty good so far. Like, the code itself is really small. Like, that's the whole code right there. Like, and this is why, like, I'm kind of like debating like how much, because the real meat comes from the fact that this right here exists, and this is the fact that you're using a linear regression. So if you want to test out multiple parts, you will basically increase, you would change this part up. You would add on to it, okay? So that's one way to fix with multiple comparisons. So let's see, did I have to talk about this? Yes, okay, I talk about it more in the A/B test. So this is when multiple comparisons get really matter, is our A/B test. And A/B test, this section 22, has a lot of lab into it, and I would definitely use this because it kind of combines the past section 20 and 21 together on how to do this. And when you hear A/B tests, whenever someone says, oh, we're doing an A/B test, you should instantly remove A/B and just think hypothesis tests. That's all an A/B test really is. And it's just, in a sense, it's a fancy name for high hypothesis tests. But you'll hear this in marketing especially, is A/B test constantly, because essentially what you're doing, you're tweaking out different parts and seeing how they affect your results. So, you know, you want to say, like, for example, if you're mailing out a new letter, you want to say, oh, is a pink paper better, a blue paper better, you know, is a green paper better, is white paper good? You know, and then having an effect size would be important because let's say, for example, it's really expensive to get pink paper and it does have an effect, but the effect is very small. You're like, oh, then it's not worth us putting out pink paper. So these are things that they would kind of consider. This is probably pretty classic in the sense that as a data scientist, A/B tests would be a really go-to that someone say, hey, we want to do these changes. And this is in the vernacular of, again, like I said, most marketing places will know when you hear A/B tests, they'll be familiar with that concept. So here's an example, classic scenario. A company wants to improve their website so that more people are likely to subscribe to their service. So what are some ways we could possibly change a website to see, let's say, for example, it's like a Spotify clone and you want more people, like you see people visit the website and you want people to join on it. Obviously, there's other factors as well as just like going to the website. But what are some things we could like change the website to encourage people to like go to the subscribe to like their Spotify clone? Any ideas? Like just kind of anything out there?
Change how information is organized on the website and presented, and also the visuals.
Good, yeah. Those are two big ones, right? One is visual, literally changing the color of the button. See, hey, maybe we change the color of like the subscribe button. Maybe that matters in how people do it. It could also be like kind of organization where the button actually lives. Is it the very beginning? Is it kind of halfway through? Is it at the very bottom? You know, and then also organization is, you know, how do people navigate through the website? You know, maybe it makes sense that they have to go through a couple pages to get to the button. Maybe that actually, like, you know, we can go with like psychology, like why this happens. Like, oh, maybe if they go into the website, they're already well invested into the website, so they'll actually go subscribe because they learned more about it. Or maybe it's that, oh, if you make it too deep, no one's going to subscribe because they're like, ah, it's too much work. They're going to just close the website. So these are things like, you know, you might have ideas of why they happen and stuff like this, but you're not sure what will actually have an effect. So this is super useful. But there's a kind of a thing in here, say when we shouldn't use this. So has anyone got an idea like when we shouldn't like do an A/B test, or at least be wary of it? I shouldn't say not use it, but like at least you should tread lightly and be super like careful with your results. This one's subtle. I don't think this is super clear, to be frank. So one thing I will say is that you should be careful when you present this is essentially how much time you're using to present this. One is, you know, like saying, you know, oh, you're getting enough users, but also like actually enough people to test it on. But also it's that if you present this to current users, it might have an effect by the fact that it's a new thing. So there's kind of two examples of this. They each have basically different names. One is called the novelty effect and one's called change aversion. So the novelty effect, as you might, you know, kind of get an idea, is that basically it's new, so people really like it. People like, oh, it's the new thing. Really exciting, right? So like if you guys are fans of Zoolander, right? Like basically the new thing that's really, and it's not that it's necessarily better, it's just that it's the new thing, right? And this happens all the time. Like think fidget spinners and stuff like that. Kids like got really excited about, you know, using these things. Flipping a bottle, not because flipping bottles are cool, but because it was like the new thing. And this is where basically like I'm guilty of this as a tech person. I get really excited when the new thing comes in, like, oh, cool, like this is new tech thing, like this is super exciting, right? And usually after like, you know, that first few months, it kind of dies off and it's like it becomes just the normal. It's like, oh yeah, that's cool, like whatever. So this is kind of related to the scenario. I carry this new scenario is that a town's been out of soap for 3 weeks. And so a new shipment comes in and business owner says, oh, like we sold all the shampoo in the first day, you know, like, oh, wow, like every day is going to be like this. Like, well, probably not, because it's just the fact that it's a new item. In this case, people can have soap for like 3 weeks. So they probably aren't going to keep buying soap in that same wealth of like a number of people coming in. So this is kind of something you should be aware of. The other part is change aversion. And change aversion, as you probably guess, is that basically people just don't like change. So like, I think of it like, you know, like it's like old man syndrome, you know, like it's like, it wasn't as good as back in the day kind of deal. And that's kind of like what you have with users. You see this all the time. Whenever there's especially very dedicated users, as you probably can guess, is that if you're really invested into the product and you love this product and they make a change, immediately you hear everyone go, why did they make this change kind of thing? Except I think for Apple. I think if you make a change in Apple, everyone gets really excited and becomes like the novelty effect. But like for most places, like it's like you have this change in it and most people like really it's like, oh, like they should have changed it this way, or like, oh, they should have kept it the same. Why did they change such a good feature, and all that stuff. So a real question is, all right, this novelty effect and change aversion happen pretty frequently. How would we avoid this? And I kind of hinted a little bit already, is you avoid this basically by waiting time. So I call it like die. It's not really dying, right? But basically you wait for the users to be replaced by new users. So especially if you start off with like a very small company to begin with, let's say you only have like 400 users and you're expanding to expand out to 5,000 users. Well, those 400 users might have very strong opinions, and at first it might seem like, oh, this isn't working at all. But as new users kind of come in and see what like basically like with virgin eyes, like not ever seeing anything that has ever been there before, then you get a real effect. And that's what you're really talking about a lot of times. So you're talking about new people coming in and seeing how they use it, not the people who are currently in it. And then the other ones, basically, it's old users, you know, they get used to it. Whether the novelty effect, they're just like, becomes like, oh, that's just what it is now. And they don't really have a strong opinion against it. Or, you know, for change aversion, people basically say, oh, well, it's not so bad. I guess it's not the worst thing in the world. So basically, the biggest thing is amount of time and being aware of your new users or your old users having strong effects on them. Okay. Any questions about this or any comments or questions on this novelty effect, change aversion for new users, old users? Okay, cool. Okay, so let's see here. I think I had a scenario here. Oh, we're actually gonna skip this part since we're running low on time, and it's basically the same stuff. So this kind of leads us to multiple comparisons. So let's say we do a bunch of changes, like we have our Spotify clone and we change the website, you know, the color of the background, the color of the button, the color or the placement of the button is the beginning, and you know, we could reorganize all this stuff. There's a bunch of things we could change. So this is ideally like what you'd want, and we can actually do this in software and say, okay, you're now part of these different groups, and we'll randomly assign you, you know, different parts. What are some issues, and this is kind of already talked about, but what are some issues by making these multiple comparisons, and then try to draw conclusions from them? Oh, Jivan, if you said something, I can't hear you.
Sorry, I forgot I was mute. I was saying like the green jelly thing that you might see an effect, but it's actually by chance.
Exactly, and that's the biggest concern. Thank you. Yeah, so it's basically, you're gonna catch more false positives. By having more chances to catch more false positives, you will catch false positives. And basically you reject the null hypothesis when really you shouldn't be rejecting it. So it seems wrong, but in fact, like you see like there's an effect, but there really isn't an effect. So one thing we can do, and this is, I'm gonna give another caveat to this in a second, but one thing we can do is, you know, we talked about ANOVA, different tests and stuff like that to be ready for this kind of thing. The other thing is making corrections. Now, I was talking to a couple people who work in the industry and said like, well, look, what does this kind of look like? This is a couple of the instructors. And they said like, in reality, it's like, no one really does this except like in like journals. And we'll talk about like why this happens. So in the curriculum, they talk about the Moroni, I never pronounce these words right, Moroni Correction, okay? And so basically it's a correction to the alpha value to say, well, what significance do you actually need? So basically you just take the critical value, right? this alpha, and you divide it by the number of comparisons you're going to make. So if you're going to make 5 different comparisons, you divide alpha by 5. And the reasoning for this basically goes to the fact that if we have more chances to, what's it called, get weirdness, we need to rate, well, I guess raise the bar, right? We need to raise the bar of like how weird something has to be until we actually say something's there. So kind of like a comparison is like if we did 1,000 coin flips, we would want to say, oh, well, having a string of 6 heads isn't super unusual. Like we want to raise that bar. It's like, oh, maybe if you get 20 head flips in a row, that's when it'd be really weird, right? And so this hopefully kind of makes sense. Like you want to, as you do more comparisons and there's more chances to essentially get false positives, you want to raise the bar on how weird things are. Now the problem with this, and I don't know if anyone could come up with this themselves, but one problem is that this alpha value, by dividing by the number of comparisons, it's really conservative. Basically, like most tests will not pass if you basically divide your critical value by the number of comparisons. So one key part is just you can use other tests to do this kind of stuff. That's probably like in reality what you likely will do versus actually trying to adjust the alpha value. And because in reality it's that most tests won't pass through. Hi. Oh, sorry, my dog's. Okay, hi. Sorry, she's getting spayed tomorrow, so I'm babying her a little bit. Okay, hi, thank you. Sorry. Okay, don't pay attention to the dog. No, she's sweet. Okay. So another method we can do here is the Holm-Bonnefieri method, and I'm actually not. I was going to like go walk you through this. I was going to write the code of like how this would happen, but in reality, you probably wouldn't be doing this in industry. And the real reason why we won't do this in industry is because it takes too long to like worry about these stuff. And in reality, it's like if you find it's a actually significant value, you just perform more tests or you try it out and see what happens, kind of deal. Especially when it's like very significant. If it's on the edge of significance, that's when you should start worrying. It's like, okay, like is there an issue with multiple comparisons? Are there other things? Do we need a larger sample size? Can we get a larger sample size that's very quick and stuff like that? Those are the things that you can do. But one strategy, if you wanted to go this direction, is this Holm-Bonnefieri method, which I have the link to the Wikipedia. Hi, stop it. Okay. And so the steps basically come down to the fact, and I have this whole part, I'm just gonna quickly say it. Basically what you do, you have multiple comparisons. Like, so you have like, your diet A, diet B, diet C, and you say, okay, here's my different hypotheses. Diet A is better, diet B is better, diet C is better. And then what you do, you get your p-value from your tests, and you order it from smallest to largest, and your p-value. And so then what happens, you basically keep making your alpha value smaller for each part. And so what this will help you do basically is, because you're doing multiple comparisons, and this is subtle, like to be honest, I think this isn't super clear like why this would work. There is proof to it basically. There's a few mathematical reasons too. But basically you order this like value, p-value to smallest to largest, and you basically say, okay, if like we look at the very first p-value, which is going to be the most significance. Oh, I'm sorry. Yeah, the most significant one. And you say, okay, this is the most significant value I ever got. And then you divide alpha by basically the Bonnefieri method, basically divide by number of comparisons. So now your critical value is going to be very small. So you're going to see, hey, does my most significant value pass the most stringent conservative tests? Okay. And so if it does pass through, then that means you don't have to, what's it called? You don't have to reject anything. If there is no value where pk is greater than this alpha value, this new modified alpha value, then you basically reject everything. You're like, cool, everything is significant. Since their most significant one basically passes through. And then you basically say, well, if it doesn't pass through, you go to the next one and the next one and the next one until basically you get something that's not significant. And basically you reject everything that is from that point. You don't reject it, and then you reject everything after that point, because everything will be above that. And so this is a nice quick way if you have literally hundreds of comparisons kind of deal. It still balances a lot of conservative parts from the very beginning. Basically your most critical value has to be your smallest p-value, which is your most significant, has to really be like significant. Like it has to be super significant. And if it is, you're like, cool, let's pass it through. And if not, it probably won't. And you move on to the next thing that's not significant. And basically that's your cutoff. Mathematically speaking, and there's a Wikipedia, like I kind of linked to, is that the right one? Oh, this is not the right article one. Oh no, that was it. I just spelled it wrong. But the Wikipedia talks about this formulation, kind of goes through a little bit more in the proof of like why this works. Basically, the reasons why it's uniformly more powerful, which is a technical term, basically it's a more powerful test. And there's a few reasons like why you can do this. It's relatively simple. It doesn't take a huge amount of computing power to actually do this. You don't have to do a whole bunch of complications. You don't have to do a bunch of bootstrapping, which is basically simulating from the sample data itself. And also the other part is more mathy, but basically it's a closed testing procedure. So these are kind of like a really nice thing. Now, speaking all to this is that in reality, you're probably not going to do this industry. It's not as common. You probably will see people just do Welch's t-tests for the majority of stuff that you have because you're looking to get a result. And usually it's like, if it's on the edge of significance, then you take a double take and say, is this actually worth us doing? Usually you only proceed with the things that are significant enough and you don't worry about making correction or other parts. You might see ANOVA, but in reality, you probably would see more closer to an F test, which is related to ANOVA by itself. But I kind of wanted to give you guys that kind of basis. And this kind of opens up the door of saying, people say, but Victor, what should I do? And it kind of comes down to the fact that there are so many things you can do. And statistics is so large, but in reality, I think of data scientists, it's much more like an engineer versus someone who's like, like my background's physics. Like we would kind of joke with physics versus engineers. And physicists will definitely tend to be much more like, it means to be academically, theoretically correct. And a lot of times engineers or the other side is experimental physicists says, but it has to work. And it's like, sure, we can do the whole numbers and make sure that theoretically going through it works, but in the end it needs to go through. A good example of this, and that's why I see the data scientists more on the engineering side. A good example of this is, I remember doing like a bottle rocket competition where you put like the bottles on like with water and you pump it up with like air and you see how high it can go. And I just remember like my friends, people I knew who were on the physics side got very technical. We're writing the equations down, like how much water we should put in and everything like that. And there were a group of people who were much more practical. They ended up being more experimental physicists. They said, oh, let's try it with half the water. That didn't work very well. Let's try it with a third of the water, a quarter of the water. And they figured it out quicker than someone trying to do the calculations. So sometimes in the end, it's nice to have these tools that other people had put together. But in reality, it's like whatever works and gets you the answer quicker. Even if it's not the perfect answer, it's essentially a good enough answer. And that's usually more valuable in industry and businesses because it doesn't matter about the perfect answer, it's about is it a better answer. Okay. So that's kind of like the end of my stuff. Any questions or any follow-ups, I don't know. Thinking.
What is, this is a silly question, but what is M and K in this formula here?
Yeah.
Is M the number of null hypotheses? Is that what that is?
Yeah, M is the number of different hypotheses you're testing. So different considerations. So that includes your control all the way through, I messed up. M is the number of alternative hypotheses. So you'd have your control hypothesis and then M is your different alternatives. And then
what is K here?
And K is basically after you order your p-value. So each hypothesis, alternative hypothesis, will have an associated p-value to say if it's significant or not. And what you do, you order those p-values from least significant or most significant, so smallest p-value, to largest p-value, least significant. And the K is the ordering of that. So your most significant p-value, your smallest one, will be K equals 1. And then K equals 2, and then so on, all the way to K equals M.
Right, okay.
Mm-hmm. Yeah, and if you're curious about this, the link to here, I don't know why this, whatever. I feel like this is wrong. Oh, I see it. Wow, I'm really tired, guys. I realize this is a different thing. But this link to the Wikipedia article does a really good job of actually showing you what this goes through. So if you kind of speak a little Vietnamese, essentially, that's what they're showing here. But essentially what you're doing, you're just ordering your p-values, and you're just going from the very beginning, your smallest p-value, and seeing at what point does this equation hold. And once it holds, you stop right there and you reject everything above that value. And then, what's it called? You don't reject anything below that. So everything above that is significant. Everything below that is not significant. Cool. Question. All right. Anything else? No? I know I kind of went over a little bit. So I'll go ahead and stop it here. And